Welcome to our presentation on note transcription. This is the team. We are all 2T1 engineers on our PEY work terms, and we're lucky enough to dodge full-time university at home. In music, transcription is the practice of annotating a piece or a sound which is previously unannotated and or unpopular as a written music. Nowadays, manual annotation is tiresome since we have the tools to automate this process. So our goal is to give those improvised and inspired outbursts of creativity an outlet that allows for reproducibility by others interested in the work. In essence, a model that identifies notes played by an instrument.
To solve this problem and achieve our goal, we decided to split our project as follows. First, we decided to create data by recording instrument audio from a keyboard. We then needed to split this data based on its pitches and label each audio file. We then uploaded these raw WAV files into a shared drive. For pre-processing, we decided to plot each audio file as a spectrogram, and then save this as a figure. Once it was saved as a figure, we then had a data set of images which we could upload and input into our CNN model. We trained our model to classify notes based on their pitch, and then performed some post-processing to translate each of the model's predictions into an English or commonly noted note. Like I said, we had to choose an instrument, and in this case we chose the keyboard. We got our data from Magenta's NSynth dataset, an open-source, large-scale, high-quality dataset of annotated musical notes in 10 families. We chose acoustic and electronic samples, which brought us down to over 30,000 4-second WAV audio files. Each audio file covered the entire range of a MIDI piano scale, which is 21 to 108. 88 classes, and they were varied over 5 different velocities, which gave us a great variation in data. Each note was held for the first 3 seconds and then allowed to decay for the final second. Once we had our data, it was time to pre-process. We had to take all of our data and split it into its 88 classes, which represented the pitch, and label these audio samples. Once we upload to our shared drive, we load into a dataset using the Torch audio module, and also included a function that allowed us to split any audio clip by its note, using the length of silence and the decibel level. After we load our audio, it was time to create spectrograms. A spectrogram is a graph representing frequency of a signal over time. We chose mel spectrograms specifically because these are supposed to represent the human ear and how it hears things. That is to say that humans are better at hearing lower notes than higher notes, and a mel spectrogram should reflect this. We saved every spectrogram as a figure. Because you can't look at a spectrogram and tell what note it is immediately, we had to download random samples and label them by hand. We then re-uploaded these samples to make sure that we were labeling correctly. Once we verified this, we split our data into 70% training, 15% validation, and 15% testing.
The chosen baseline model was PyTorch's random forest classifier. It was chosen because of its intuitive majority voting method of returning a classification given an input. N estimators is the number of trees in the forest, depth is the max number of branches in each tree, while random state allows for reproducibility of results. We found validation and test accuracies for dataset configurations of 10, 20, 30, and 60 spectrograms per class. More images correlated with higher accuracies, while more trees in the forest had the tendency to cause overfitting to training data, giving us lower validation and testing accuracies.
For the primary model, we use the CNN because it's great for image classifications due to its automatic feature detection, so that the neural net will learn all the small differences that the spectrograms contain. After training for roughly 12 epochs on a 5,000 dataset, we achieved a training accuracy of 92.9%, a validation accuracy of 92.1%. And then here below is the diagram of the CNN. The model has 9 layers total, including 2 convolutional layers, 2 maximal layers, 2 dropout layers, 2 fully connected layers, and 1 output layer.
What we would do following that final output is translate each MIDI note to the musical alphabet that most are familiar with, A, B, C, D, E, F, G. That much we've done. To go beyond what was accomplished in this project, we would improve architecture to accept notes of different length and classify these relative durations, and also accept audio files with more than one note. Another obvious step would be to expand to instruments other than just the keyboard or piano. Lastly, these notes would be plotted on a document of sheet music, which the user could save for later.
Here is the model demonstration.
To demonstrate how effective our model really was, we needed some new piano data. Of course, none of us can actually play the keyboard, so we found a random virtual keyboard and pushed some random keys. We counted the locations of the keys so we'd be able to later translate the notes into their common notation. We loaded all of the functions and the model, including some pre-processing steps, such as the minimum silence length and the decibel level. This allowed us to take that long audio clip and split it up into its individual notes so that our model could identify them. At the very bottom here, you can see what our model has predicted. Our model predicted every single note correctly except for the lowest note, note 23, which it predicted as note 25.
Quantitative results. The test data was a random sample of 9 audio clips for each class, totaling 792 samples. This test data was only used after the model had trained. Similar results between validation, training, and testing indicates a level of generalization and not too much overfitting. As seen in the graph, after 12 epochs, the model is stagnant and confirmed that we reached the max possibility of training. To better identify why the accuracy plateaued, we created a histogram to highlight classes that were underperforming. We noticed that the model performed worse on lower notes, and to better understand why, we turned to qualitative analysis. From looking at the lower note spectrograms, we noticed that there was a greater variation to the point where they looked like completely different notes. Also, that notes next to each other looked very similar, as seen with notes 41 and 40. Another observation, we noticed that even due to this variation, the model output wasn't exactly random, and in most of the failed cases, they were only 1 or 2 notes off. If we add this tolerance to the model, the new accuracy was 96%. The model had overall high accuracy with low overfit and was close to the majority of wrong cases. With this, we conclude that the model was successful. Other limitations we found came from the training data. The dataset had a certain format and needed to be 4 seconds long. We noticed that any variation to this format did worse, as well as shorter notes with loss of silence did worse.
Overall, we successfully developed a neural network that could classify notes based on their spectrograms using a CNN model. However, we also noticed that the spectrograms varied significantly as a result of slight differences in data, which means an equal amount of time must be put into the pre-processing and the post-processing stages. By incorporating the considerations we highlighted in future iterations, we believe this application of machine learning could make music theory more accessible for music enthusiasts and professionals alike.